And let's go back to residue, right? To residue calculus, right? So or calculus of residues. Right, so if you have any trouble seeing or anything, please let me know. Remember that, yeah, YouTube has a little bit of a delay, so go on Zoom if you want to interact. Okay, so we have a function, right, defined in a set omega prime, right? Basically, where omega prime is obtained from omega by removing we say A1, AN, right, where the isolated singularities of F. Right, so F is analytic in omega except in those points, isolated singularities of F. Right, so analytic. Okay. And we defined, right, and we were interested in understanding the integral of F around curves that go around some of these singularities. Okay, so definition, we defined the residue, right? I mean, I'm just revisiting things that we've done. The residue of F at AJ is, right, the number Rj such that let's see, minus Rj z minus Aj has a derivative, or as a primitive, or is the derivative of a function. In an annulus. Right, by the idea being that in curves that go around AJ in a sufficiently small annulus for, sufficiently small delta bigger than 0, right? That the integral of Fz minus Rj over z minus Aj is 0, right? And so it needs to be the derivative of a function. Okay, and we write, right? We write Rj. Right, we use this notation, residue z is equal to Aj of f of z. Right, and the point is that now this tells us the integrals of all the curves of this function around isolated singularities. Okay, I just need to pick up some images. Sorry, all right. Hopefully it's working well. Okay, so okay, and so I just saw something on the chat. Okay, I don't know if everything is. Why are we defining this like this? For no, I mean, just to yeah, there's no real difference, right? By doing it this way, we just I'm just like highlighting that this is the same thing, right? But it's just maybe, yeah, there's maybe an advantage, which is that, right? So the way we defined Rj was as, was something with respect to the period, right? So that the integrals around f become right. So that the integrals around f become basically 2 pi I Rj, the integrals of f around Aj, right? Defined this way is because then it becomes easier to compute oftentimes, right? So I guess that's the best reason to give for the definition, right? But it's the same thing, right? Because if the integrals then become all 0, then it needs to be the derivative of a function at this around this annulus, and right, because you can define, you can take the integral to define the primitive that way, as we've done a few times already. But if you, maybe the best way to think of it is, let's say, and we're going to do this a bit. Let's say I write f of z as just a sum of polynomials and both with positive and negative degrees, right? Then all the polynomial factors will have a primitive, and let's say 1 over z squares and z cubes and so on will have a primitive. And so in order for the whole function to have a primitive, usually there's only a problem at the 1 over z term, right? And so once you fix that problem, you sort of know that, that then this becomes as a primitive, and so this is an easy way of computing the residues. Okay, this will be more clear in a second. But they're completely equivalent, these notions. Okay. So now, right? And so we have that for, if I take a curve, let's say in particular, I take a curve, say a circle, right, centered at AJ, right, and with radius, I just want it to be inside this annulus. So let's say I do it, over, say over 2, just to make sure I'm inside the annulus, right? I don't touch any other singularity. Okay. Then right, maybe I should use subscript j just to be a bit more complete, right? Then, the integral of f of z around this curve, dz, right? So should be, will be equal to, right? Because the integral of the whole thing is of course 0. Then this will be equal to the integral of rj, right? 1 over z minus aj dz, right? And so this is just equal to 2 pi I rj, right? And so, I mean, another way of writing this is that, right, this means that the residue z equals aj of f of z will be equal to 1 over 2 pi I, right? The integral of around this curve of f of z dz. Okay, and so, right, even though I picked here a curve, a specific curve, it's clear that if I pick another curve that doesn't go around any of the other singularities and just goes around the singularity aj once, I get exactly the same thing, right? So the residue gives me the value of the, it gives me the value of the integrals. But there's already sort of something, there's something here that I want to be, before we go on with any calculation, I want to bring some attention to the intuition behind this. Right, which is that, the residue is basically, you can define it as this integral, right? Because as something with respect to the period, or maybe let me put it this way, right? So we define the periods, right? We saw already before that if a region wasn't simply connected, if it was multiply connected, if you have a function, then all you have to understand is the integral of, for each point, for each, say, part of the complement of omega that is unbounded, right? All you have to understand is the integral of f on a curve around it, right? And we call these the periods. And then the integral for any curve was just a linear combination of these periods. Okay, so that gave us some kind of like linear properties of the integral, that if we want to compute the integral of a specific function over any curve, all we need to compute is these periods. Okay, this was already, I think, somewhat surprising and a powerful technique. Now, the other powerful idea, like sort of hidden, I mean, I wouldn't say hidden, but present here is the fact that, right, because the integral, like let's say that instead of, let's go into the simpler setting in which is the one that shows up most, right, in which the function is analytic in a region except in isolated singularities, right? And we have these A1, AN isolated singularities. Okay, then because we know that the integral of 1 over z minus aj is 2 pi I in a curve around the singularity, right? We know quite a bit about this integral. We know that if we defined rj, right, to be the number such that, the integral of f of z around that curve and the integral of rj over z minus aj around that curve are the same, right? Then, right, so we define rj to be like the period over 2 pi I, right? So then if we do that, right, then it means that the integral of this, of f of z, right, minus rj over z minus aj becomes 0, okay? And because the integral being 0 is the same as being the derivative of a function, right, at least in a nice set, we've seen this a few times, right, then it means that sort of in order to compute integrals of functions that are with isolated singularities at least, and around, you know, on curves that potentially go around those isolated singularities, basically all you need to understand is what happens at this part of the function that has the 1 over z. At the 1 over z in, right, if you think of the function as, you know, as poles and zeros and so on, you really only care about this part, this 1 over z minus aj. And so this will be, the power of this is that you're going to be very easy to compute the residues. You will not need to integrate at all. And then you'll know the value of all the integrals. And this is what's going to make everything extremely easy to compute integrals. Okay, so just to give some, you know, bird's eye view of sort of the idea that's core here. Okay, let's see if there's any questions. Oh, there was some earlier questions that I can answer later. The radius is not, I just wanted to make sure, yeah, someone asked if the radius was important, there was delta J over 2. No, I just want to make sure that it's, you know, there's that it's inside the region where this function, you know, is the derivative of something. So I just want this to be smaller than delta J. And so I picked delta J over 2 just because, right? But it's not important at all. It can be anything. Yeah. Right, the point being that if you have a j, there might be another singularity, say a 1 here. So I want to restrict to inside of that. And then I call this, say, delta j. And I just wanted to make sure that we were in somewhere inside of that. Right? So I called it delta j over 2. Okay. All right. Thanks for the question. So, okay. Okay. So where was I? So, right? And so we have this, right? Basically prove the what's called the, you know, the theorem of the calculus of residues. Like it's completely proven, right? Because let's say, I mean, let me just write it. Let's say that we have a curve, right? A closed curve that's inside omega prime, right? So what do I mean is, like, you know, you should just think of, it's just a curve inside omega, but I need to make sure that the aj is not in the curve for any j, right? For any j. Because otherwise it's trouble. Okay. And now let's say that the curve is homologous to 0 in the big set omega. Okay, so the only ways it might not be homologous to 0 in omega prime, because, you know, it might go around these isolated singularities aj. Okay. Okay, so let's say let Cj be a circle around, I should say for each j, okay, let Cj be a circle around aj small enough so that no other ak is in it or it's inside, right? So I have aj, maybe I should use another color to draw pictures. I have aj, and now I take a circle so that, you know, all the other A1, A2, and so on, all of them are outside. Okay, okay, then clearly, you know, because gamma is homologous to 0 in omega, then, you know, obviously we have that this is homologous to, right, the winding number of, you know, right? I mean, this is how we got to the periods and so on, right? Okay, so for now, nothing new, right? And so, okay, for now we're just sort of revisiting what we did when we talked about multiple connected regions, right? So we have that this, right, is equal to the sum over this, right? Where the periods, this is how we define the periods, okay? So we define the periods, you know, it's just the integral on Cj of fc dz, right? But now remember, the periods were equal to 2 pi I, these residues, right? And so in particular, because of this, we have that right? We can rewrite one over 2 pi I sum aj, and then here is the residue. Residue z equals aj f of z. Okay. And of course, you know, this is basically what we call calculus of residues. And maybe the point that I should make is this is very useful, and I'll try to convey this to you by showing you examples, very useful for poles. Because it'll actually be very easy to compute these things for poles. Okay, maybe another point I should make is that, you know, by now we've seen again this idea over and over again, but it's worth maybe recalling that the right, usually we take a curve gamma such that the winding numbers of anything even are equal to either 0 or 1. Right? We take like a circle or a curve that just goes around once, right? But I mean, not always, of course. Okay, and I'm not being too worried about whether there's, you know, whether this sum is you know, indexing this sum properly, right? Because of these arguments that again we've seen quite a few times, that if I have a curve, right, as inside where f is defined, then f can only have right, finitely many zeros inside. If if f is analytic on something outside of this curve, because otherwise it would be identically 0, and then sort of these sums become all finite. Okay. Because they are, right, the singularities are isolated, not the zero, sorry, the singularities are isolated, so once you put a curve, that can't be, you know, there can't be infinitely many of them. Okay, so let me see if I can convey to you why this is so useful for poles. Okay, so let's say, let's take just one singularity, right? Because I mean, we now, the function can have many isolated singularities, but we can restrict to just looking at one, right? This becomes now a local, the understanding the residues now becomes a completely local thing, right? And in particular, understanding now an integral that might go all over in the place, like all over the place in the domain, now reduces to a question about understanding these residues, right? Which is something very, very local, right, around each point aj. So let's say, okay, let me switch to something else. So let's say, okay, let's say that f has a pole at a, right, at z equals a, right, and of order, let's say of order h. Okay, then what this means that, you know, z minus a h f of z is analytic, right? Right? So this function is right, it's analytic, and so we can take this, right, we can take the truncated Taylor expansion that we took of this, right, and then we can just divide by z minus a to the h everywhere in all the terms, and we get an expansion for the function that has a pole, right? So we've done this before. Is analytic, I mean, I should say in a neighborhood, yeah, in a neighborhood of a. Right? I mean, the other isolated singularities will still be singularities, of course, if it has any, but at least in the neighborhood of A, it will be analytic, right? And so I can take, at least in the neighborhood, right? Or I can take f of z, right, to be equal to, you know, some constant, right? So these are numbers, some constant bh z minus a to the minus h, then plus b h minus 1, say z minus a to the minus h minus 1, plus, and so on and so forth, right? And then there's a term, let's keep track of the last few terms. There's 1 plus this, right? Where this function is analytic in in a neighborhood. Right? We've done this before, but how do you get this? You just take this function here, right? You just take this function here, and you do this Taylor approximation, the finite Taylor approximation that we saw, and then you divide by z minus a h everywhere, and you get this expansion for f of z, right? If you were now to multiply this by z minus a to the h in each one of these summands, you get exactly this thing that I underlined in green here, right? And then you'll get a bh minus 1, z minus a, and then a term with z minus a square, and so on, and then the last term with an analytic function times z minus a to the h, right? Which is exactly what we saw in this finite Taylor expansion. Okay. But so what does this mean, right? In the neighborhood of a, right? All these functions have primitives, right? This, right, has a primitive. Okay, let's say, I mean, we should think of h bigger than 1, right? I'm isolating, I'm not thinking of this term as being the same as b1, right? But all the terms that have a term like z minus a to the minus 10 to the minus 9 and so on, all these terms have primitives, right? By Cauchy theorem, and I mean, you've seen these things, then this term too, right? The only term that is problematic, right? And you can think in terms of having primitives, or you can just think in terms of taking integrals right now in a curve around A. Sort of the only problematic term is this one, right? All the other integrals go to 0. The only term that is problematic is this one here, right? This is the term that doesn't have a primitive, right? Around in a neighborhood around A, and if you integrate, it doesn't give 0. And so immediately you get that if you remove this term, then the function has no problems. Then the function becomes, becomes a derivative of something. And so B1 is the residue. Right? Why? Because if I take f of z minus b1 z minus a, right, then it's the derivative of something, of a function and then in the annulus. Right. And so this means that once we are able to do this expansion, then immediately we get the residue, right? So the residue is just B1. There's no need to compute any integrals. Of course, we need to do this expansion, but there is no need to compute these integrals. Okay? In particular, maybe I should make another point. Okay, there was some question. Okay, maybe I should draw a picture. There was a question about, because I started with a curve that was homologous to 0 in omega. Yeah, okay, so let me draw a picture. The picture to have in mind, sorry if that wasn't clear. The picture to have in mind is this, right? There's some omega. I mean, it's fine if it's simple connected or not, it doesn't matter, right? And now we have a curve, maybe this, right? And the curve is homologous to 0 in omega, right? Doesn't go around the part that's not in omega, that little hole in the bottom. But the function has removable singularities, right? So the function will have removable singularities, maybe here, 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 here. Oh, sorry. Right, the blues, they are removable singularities. Right, and so the function f is really only, right, and so omega prime is omega without the removal of singularities, and the function f is really only analytic in omega prime, not in all of omega. Right? These are immovable singularities. Okay, yeah. Thanks for the question. Okay. Yeah, I should draw more pictures maybe. Okay, I'll try to keep that in mind. And yeah. But yeah, thanks so much for the question, because it's much better if I get to still have the chance of drawing the picture, even if 5 minutes after. Okay, so this means that now we can actually compute the residues very, very easily. In particular, right, and this is sort of maybe the most striking, is like, right, in particular, if the pole is simple, right, what do I mean by the pole is simple? The order of the pole is 1. Then it's even simpler, right? Because then all you have is that f of z is equal to b1 z minus a to the minus 1 plus some analytic function, right? And then b1 is the residue. It's almost trivial to compute this, right? Computing the residue becomes almost trivial, because all you have to do is to take z minus a f of z, right? Now what is this? This is b1 times z minus a phi of z, right? Evaluated at z equals a, right? Because if I were to do this, what do I get, right? What is this equal to? Z minus 8 f of z is equal to b1 plus phi z, z minus a, right? Evaluated at z equals a, this is equal to b1, which is the residue. Right? And so now it allows you to compute residues, extremely easily, at least for some function. So I'm going to use an example, that's in the book, so you can go look it up there if you like. So let's say I take, just sort of as a super simple example, let's say I take f of z equals to e a b, say z minus a, z minus b, right? And this is a simple pole if z is different than b. If z is the same as b, is not a simple pole. It's still easy to compute, right? But I mean, you should go look at the book on how to do it. It's just instead of taking 10 seconds, it takes maybe 40 seconds. Okay, but let's stay with a different than b, just to sort of drive home the message that at least when they're simple, this is just really, really trivial, right? So what is the residue when z is equal to a, right, of f of z? Right, all we have to do is grab that function, multiply by z minus a, and then evaluate it at z equals a, right? So what is this function multiplied by z minus a is just e to the ab z minus a, right? Evaluated at z equals a, but this is just e to the ab. What did I do? Oh, b. A minus b, right? And the residue, there's of course another pole at b, right? The residue will be exactly, the same thing, but now it's b minus a, so I'll just write it. E to the ab, b minus a, okay? And so, okay, so we computed the residues really, really quickly, but what does this tell us? So let's just look at an example. So let's say that a is right here, b is right here. Okay, and now I draw a curve. I take a curve that maybe goes around a, I guess it already went twice, and then let's say, okay, so I have, hopefully I won't make a mistake. Let's say that I have this curve, so it went like this, right? I have this curve. Okay, and now I draw you this curve. I could give some equations for it, right? But let's say I have this curve and I ask you, okay, what is, right? What is the integral, say 1 over 2 pi I, just, so that things become nice, of f of f of z, or let's say e to the ab z minus a z minus b dz around this curve gamma, right? And I ask you to compute this, right? I mean, if you think about it, this sounds ridiculous, right? To compute something, you know, Cauchy's theorem doesn't quite work, right? It seems like a humongous mess, right? But really, now with calculus of residues, this is almost trivial, right? So the curve goes around, if I did this correctly, goes around A, I believe, twice, right? So the winding number of this is 2. The winding number around B is -1, right? Goes once, but the other direction, right? So it goes around A, goes like this, then it goes around B the other way, and then it goes around A one more time. And so all this is just twice times the residue at A, E, A, B over A minus B, minus, oh, this is -1. Right, minus I guess the residue once times the residue at B minus A, right? But this is just 3 times E to the AB, A minus B. Okay, if B is equal to A, the residue takes just 30 more seconds to compute. I recommend just try it before you go look in the book about how to. Oh, I realized that on YouTube this was not showing, but okay, you can see. I think now it shows up. Okay. Okay, any questions? No, I don't think there's anything new. Just to convey how easy it becomes to compute integrals now, right? Because essentially, the problem with the integrals is completely at the 1 over z term, or the 1 over z minus a. Okay, so now before we finish, I guess I have 3 minutes. We finished at least this part of the lecture. I just want to say a couple of things. One is that Cauchy integral formula comes for free, right? So now we can prove Cauchy integral formula almost for free, because take this analytic, right, and take omega 0 mod, sorry, not omega, sorry, gamma homologous to 0 mod omega. Okay, and now let's look at the function f of z, z minus a, right? This clearly has an isolated pole. Let's say that a is inside omega, of course. Fc minus z minus a as a simple pole, at a, right? It's also very easy to compute the residue, right? Because what is the residue of this function? Again, you multiply by z minus a, you get f of z, then you evaluate at z, you get f of a. Right? Trivial thing to compute, exactly the same way that we did before. But now if you look at the theorem, right, what it says is that, now the residue, the theorem of the calculus of residues just says, okay, so 1 over 2 pi I integral around the curve, right, around this curve of f of z, z minus a dz is equal to the winding number, right, of the curve around A times the residue, z equals A of f of z, z minus A, right? But what is this? This is just the winding number times f of A, and this is Cauchy integral formula, right? We just proved Cauchy integral formula, I mean, came for free, essentially. And so now in the last minute, let me just say that we proved all this stuff for like Cauchy's theorem and so on, very much targeted for complex analysis, right? And if you want to understand simply connected spaces for higher dimensions and so on, you need other definitions. Basically, you want that when you have a path, you can contract it continuously to a point, right? I mean, I talked quite a bit about this, and so you'll see some of this in topology, and if you pursue more studies in algebraic topology, you'll definitely deal a lot with this. Now, maybe something worth mentioning in case you've been, studying from other books, which you should just explore how other books do it and other ways of explaining the material. Many times Cauchy's formula or Cauchy's theorem is proven by taking the path to be the boundary of some domain, right? For some nice domain omega, right? And if you have your curve being the boundary of a nice domain omega, then you can use things like Green's theorem or Stokes theorem type things, where you get integrals around, right? Integrals around the boundary can be given by formulas like Stokes, Green's theorem, and so on, as integrals of other functions in the region. And then you basically show that the integrals in the region are zero, and so the integrals in the boundary also need to be zero, right? This is a common strategy. Now, the strategy that we take allows us to not have to worry so much about whether all nice, curves are boundaries or not, or how do we deal with curves that are not nice boundaries of nice sets, or they wind around each other more than once, and things like this, right? But this is another way of talking about Cauchy's theorem that I think is worth mentioning. And it connects to things, yeah, like Green's theorem and I mean Stokes theorem, or at least those types of statements. Okay, so with this I'll finish this first session, and then we will come back in 10-15 minutes to do argument principle and start with convergence of series and sequences of analytic functions. All right, if there's any question, I mean, I'll be here for these 15 minutes, and yeah, happy to answer any questions that might arise.